Okay, well, we will get started here on our first invited speaker of supercomputing. It's my great pleasure to introduce to you Charlie Catlett. And my whole experience with Charlie was an email conversation about how to go camping in Australia. So I looked up some more factual things to say about him, and I discovered that he has 3 senior positions. He's senior computer scientist at Argonne National Lab. He's senior computer scientist at the Computation Institute, which is a joint venture between Argonne and the University of Colorado. And he's senior fellow at the Harris School of Public Policy at the University of Chicago. But much more interesting than all of that, he is lead of the NSF-funded project called Array of Things, which employs 500 intelligent sensors around the city of Chicago to check on conditions there. And he is the founding director of the Urban Center for Computation and Data, which brings together a very diverse set of practitioners to understand how computation, data analysis, and embedded systems can be used to understand how cities operate. And so I'm very excited to learn about some of this work in the talk. But before I step down, I want to say to you in the audience that if you go to Charlie's talk on the online conference program, you will see that there's an Ask a Question button. And if you click on that, you can post questions, and you can vote on questions posted by others. So at the end of the talk, we can look to see if there are some really popular questions. All right, and so I'll turn the floor over to Charlie.
Thanks, Liz. Just checking the microphone. Thanks for coming. I want to spend 30 minutes or so telling you about what we're doing in Chicago, where it's a set of efforts that started about 5 years ago, where I had the opportunity to ask the question, what could we from computational sciences and computer science do that would be able to combine interesting research with actual challenges that cities have. And so I began working with the city of Chicago, and we've since been working with other cities as well. So I want to kind of give you some background on what we're trying to do and spend a lot of my time really talking about the different kinds of data that we're working with, and the bulk of the time talking about the Array of Things project. So I'll start by saying, I don't typically use the term, I don't even like the term smart cities, because it has this connotation of cities just need to be more efficient like factories. But in fact, if you look at cities, and there's some maps up here, it's a very different experience for individuals in cities depending on where they live. There's this very strong neighborhood effect which comes out of 100 years of research at U Chicago. And I just want to walk you through these maps to give you an idea of what we're talking about with neighborhood effect. On the left-hand side, you see life expectancy, and the top is Chicago. And the difference between dark red and light yellow is 14 years. So your neighborhood affects your well-being and, in fact, your life expectancy. Below that is Philadelphia, which is actually even more of a span. That's a 20-year difference depending on where you live in Philadelphia in your life expectancy. Then one over, at the top you see asthma in Chicago. Notice the dark red areas. You'll see a pattern with those dark red areas in Chicago, as you'll see in other cities as well. On the bottom is asthma rates for youth hospitalization in Boston. And then you have urban heat island in Chicago, and below that, a visualization of public transit, where if you live in one of those green areas, it'll take you about 30 minutes or less to get into the city center with public transit. If you live in one of the gray areas, not counting the lake, which is also gray, but one of those gray areas, it'll take you 90 minutes or more to get downtown on public transit. So when I think about smart cities, I don't so much think about optimizing the green parts, but spreading the green parts to eliminate some of the red parts. And these are examples where we have administrative data or healthcare data or other data about the city that's fairly easy to get a hold of. On the right-hand side, the last one there, that's a crime prediction algorithm that we were experimenting with some of the algorithms the police departments use that's 866 census tracts for the city, to predict on an hourly from 1 hour out until 72 hours out the probability of a violent crime happening, assault, a violent crime or robbery happening in that census tract, with red being way more likely than the rest of the city and green being way less likely than the mean across the city. And we were specifically looking at weather and its impact on crime, and other people have looked at air quality and impact on crime, and I'll come back to that when we talk about measurement. Now, you've heard all the statistics, 70 or 80% of GDP is generated in urban areas, and I don't just mean the million plus cities, I mean in urban areas with tens of thousands to millions of people. Energy use primarily in cities or related to cities. I was part of this PCAST report working group that worked all of last year. We ended up sort of looking at three facets of cities that you see in this table here, where you have the components of cities in the rows, and then just thinking of cities in terms of how resilient they are in terms of their use of natural resources or their impact on climate. And then in the middle, how easily people and goods and ideas flow through cities. And then the third part, which is about those red spaces on the map, is a city that enables people to do what you come to the city to do: raise families, have jobs, make businesses, et cetera. And it turns out that when you think of resilience, it really cuts across these areas. And when we think of resilient cities, in our community, our science community, the physics and the atmospheric sciences, air quality, transportation, et cetera, we typically think of the bottom left side of this framework that the Rockefeller 100 group developed, and not so much on the other three of health and well-being or economy and society. Is a city an equitable place to live? Is it a just place to live? And then leadership and strategy in the upper left. Now, Chicago's one of the Rockefeller 100 cities, and we did this all-day workshop that the mayor put together with the new chief resilience officer. And we had 100 people in the room from different walks of life in the city: research people, government people, community organizers, artists, et cetera. And we broke into these working groups of 10 people throughout the day, where we took each of the 12 areas that you can probably barely read on this chart here, and we ranked the city. How is Chicago doing in that area? And then sort of rolled them up into the four. And here's how this group, anyway, thought Chicago was doing. Sort of, C+, maybe B- in the top two, really well in infrastructure, communications, et cetera, and really poorly in social and economic aspects of the city. So to me, that tells me that our effort to try to support social and economic sciences with computation is a well-served effort. If you really want to make cities resilient, we have to sort of go beyond the climate and airflow and water flow. Not that those aren't important, but also think about the social aspects of cities. Now, in the DOE, there's the Exascale program, and I have a team of people I'm working with at 5 different labs, and we actually put a proposal in for a set of coupled models. And I want to use this as an example to sort of frame out the kinds of data that we're working with and why we're doing measurement. Well, we just chose 4 different models, a couple of agent-based models, transportation and social economics, a large eddy simulation for urban atmosphere to try to get that down from a kilometer resolution to maybe 10 meters or so, and see how that interacts with buildings. And the idea was, in this first year of the project, the idea is to quantify the data flow between those models, and the types of data between the models, as well as between the real world and those models. And you can see at the bottom sort of these 3 facets of data where I'm categorizing them according to data that's pretty much open, like the building footprints when they were built, the roads, the neighborhoods, assets of the city. In the middle, data that you would get through sensor networks, which I'll talk about in more detail. Now on the right-hand side, human subjects data. You can't really address education or crime in a city if you don't look at data about people. And so you can't just do that with sensors, and you can't just do that with open data, but you also have to have a way to bring in sensitive data, human subjects data, census data, financial data, economic performance data, et cetera. So I want to essentially take the next few minutes and go through these three areas with a large emphasis on the middle one, just because that's where I'm spending most of my time lately. When we started working with the city, we found that there was lots of open data. You know, hundreds, maybe 150 cities by now have open data portals in the US alone. Counties and states have open data portals. There's open data, you know, the federal data.gov site. And what we found when we talked to scientists who had research questions that could use that open data is that largely they weren't aware that it exists, because all these open data portals are, and this is, you know, one audience that at least some of you remember this, they're sort of like the anonymous FTP servers of our day. They're great if you know the data's there and what you're looking for and you want to go pick it up, but there's no Gopher or Archie, much less a web, to try to help you find open data. And then you want to discover that data and analyze it and explore it. So we built a system with some funding from the National Science Foundation and from the MacArthur Foundation to essentially go from this on the left, which is interesting maps of data, in this case, City of Chicago. Even, you know, interesting animations. The one that's in the middle there, I don't have a pointer, so not the purple one, not the green one, but the other one is a snapshot from an animation of snowplows as they move through the city, because it turns out many cities, including Chicago, have GPS on all their vehicles. So you can watch the snowplows work through a 2-day blizzard with that animation. And that's sort of interesting, but what cities that we talk to really want to be able to do is move from reactive policy to proactive policy, to see trends before people even notice them and start to complain, and actually take action on them before they become the kind of problem that's way more expensive or maybe even intractable to solve. And so what they want to do with their data is largely predictive analytics and some optimization. An example of that on the right-hand side here is food safety inspections. In Chicago, there are about 15,000 food establishments, you know, grocery stores, restaurants. There are 32 inspectors. So each of those inspectors has to do 500 establishments a year. And the typical way they've been doing that is a random walk through the 500. The health department came to the city chief data officer and said, can you help us do a better job of our food safety inspections, get through restaurants faster? The idea of a food safety inspection is to find and fix safety problems. So the first thing that the city then did, with some help from us and from private companies like Allstate that contributed expertise, was to start to rank the restaurants high, medium, or low as a risk of food safety violation. And that came from a lot of different data sets, not the least of which is previous inspections, but there are other leading indicators that were used. And here you see a 60-day double-blind trial where it's the vertical is the number of problems found, and across the horizontal is over the course of 1,200 or so inspections. The red is the random, and the blue is the targeted inspections, where we just reordered the inspections. And you can see that, well, the average there is about a week ahead of time catching those violations. And that's not a long amount of time, but in a week, you can have a lot of food safety issues that impact people's health and the economy. So a week is actually a pretty long time. Now, Sven Leifer and Prasanna Balakpresh and Stefan Wild and others at Argonne in our applied math group have now been working with the city to take this one step further and do, you know, the traveling inspector problem, essentially, try to optimize their flow through the city. And really we're trying to push that blue up and to the left to catch violations much quicker. Now, if you're wanting to do a project like this, or like the one I mentioned before, which was looking at crime and weather, then where do you find the data? So a typical scientist would have to go out and look at all these open data portals. What we did with funding from NSF and the MacArthur Foundation is build this portal here that takes a bunch of open data from Chicago and other places, pulls it all together into a geospatial database, and then provides APIs to build websites like this, where I'm saying, okay, I'm interested in food safety in Chicago, and specifically down near you, Chicago and Hyde Park. So I'm just going to look for calendar year 2016 and say, what data do you have available about that place during that point in time. And I get this list of 20 or 30 different data sources. I can see the sort of temporal signal along the right-hand side. But I'm looking for food safety, so I'm going to go to food inspections and look at those. And now I'm just going to get not just the temporal map, but also a sort of density map of how those inspections go across that area of the city, Hyde Park, Kenwood, around Chicago. And then I want to say, well, I know the structure of the data because it's all in there. And so I'm going to target and just say, where are the food safety violations that were based on a complaint? So I add this filter, and then I'll rerun this and get a more targeted result. And now I'm ready to do whatever science I wanted to do, but I haven't had to pull the data together in terms of space and put it on a single timeline. So I can just download this data and then go off and do my analytics. And this is the kind of thing that people who study cities need, because you don't want to spend 60% of your time just finding data to answer your question. You really want to get through the data and as quickly as possible start doing the data analytics. Now, because this has an API on top, the city then built a different interface, whereas ours was aimed at social scientists or policymakers or any other kind of scientist. The city said, well, let's do something for residents. So they built their own portal on top of our system that's aimed at residents. And in fact, all this is running on Amazon Web Services, and you can go into the web service marketplace on Amazon for your city, and with a click you can implement all of this in your city. So that's sort of an open data. We're doing a little bit of work that's just started on sensitive data, where the idea is protected sharing of data that has laws about how it can be shared, and you have to keep track of who uses it. And there are systems that do this, but they're really sort of mostly developed in the 90s or maybe 10, 15 years ago, not easy to use. And so what we've been doing is we pulled in the Globus team, Ian Foster, and Julia Lane's been leading this from NYU with her connections in with the US Census Bureau. So we have some funding to build a prototype system that not only allows you to share and control data, this also runs on AWS, but on the Gov Cloud, because it has to be FedRAMP approved. If you don't know what that means, I envy you. It's about security and control and process, keep things safe like your census data. So we wanted to go a step further and say, could we employ some of the benefits that people are getting from shopping on Amazon or on other social network sort of things? Can we make this more fun to use and even helpful to use, so I can log in and look at what I've done before and other data sets that other people have used? Maybe I find a data set, I look at a sample of it and say, yeah, that's protected data, but I could really use it for my research, so I can put in a request, get access to that data for my project, and then before I can export it, get permission from the data owner. And the data owner in this case gets to watch and control who has access to the data and maintain that control, without which they wouldn't be willing to share it with another agency or another group. We feel like this is something that I discovered at University of Chicago was really needed a couple years ago, because we have at least a half a dozen groups that have very sensitive data from, for example, Chicago Public Schools, and they all manage it differently. And if any one of them messes up on the security of that data, everyone is going to suffer, because the Chicago Public Schools will say, well, you can't have our sensitive data anymore. You're not collecting it, protecting it. So even on campus, we're looking at ways to use this kind of a facility to help people share data. Okay, so now I want to talk about the Array of Things project, but I want to come back to this crime prediction. That's a slider along the top, and so we wanted to be able to slide out 72 hours and get this. The purpose of this, we were working with a former Chicago cop, and then he also was the chief data officer for the Chicago PD, and we were just trying to figure out if we could reproduce the urban legend, if you will, among police officers that the first warm spring weekend turns violent. Not sure where in the city, but somewhere in the city there'll be a bunch of violence when it's the first spring weekend. So we tried to look at the impact of weather on our ability to predict crime. And here we had millions of crime records over the course of about 8 years for the city of Chicago, with detailed time of day and address, so we knew exactly where they happened. And yet we only had a half a dozen weather stations around the city. So although we have 866 areas here that we're predicting on, we're really kind of smearing weather in a way that we all know from living in cities or even elsewhere. It could be raining in the north part of a city like this, and then 10 miles south, it's a very different situation. So you need more than 6 places in a city like this to do weather. And this was one of the things that got us thinking about measuring cities to provide higher spatial and temporal resolution of data for things like weather. Another example, and as I mentioned, lots of groups are doing research on human decision making and influenced by things like air quality. But here's a map of Chicago with the air quality, EPA air quality stations, and those circles are tens of square miles where we have zero information about air quality for those neighborhoods. And if you look at air quality in cities, you also know that, like weather, it isn't uniform across the region or even across the city. You have parts of the city, like underneath the question mark in the bottommost circle there, where there's a significantly worse air quality regularly than other parts in the city. So how do you diagnose that if all you have is data about, I mean, it's certainly helpful to have what kind of buildings are there because people spend time in buildings, but if you don't have air quality data, how do you actually figure out why people in that area have higher asthma rates than other parts of the city? We proposed the Array of Things project, and by the way, we don't have 500 yet. We'll have 100 by January or so and 500 by 2018. We proposed it and we set out to have a series of workshops, actually over about 3 years, with these different science areas where we would call people together from different universities and national laboratories and say, hey, if you could put 100 or 1,000 sensors across the city to pursue your research questions, what would those sensors be? And that set of workshops resulted in 2 things. One, the actual configuration of what sensors are in this version of the device that we're putting out in the city right now. The other is a recognition that we need to go beyond just sensing temperature, humidity, carbon monoxide, et cetera, to putting HPC right down into the sensor device so that we could detect more subtle things like maybe an accident, or which is not so subtle, but a near miss, which is more subtle. Or maybe as we talk to the social scientists, we want to decide to put and do image processing on a park and say, well, we just did this new park or this change of this intersection, added a mini park. How does that affect the pedestrian flow or the vehicle flow through that place? Is it a sticky place? Do people go there and hang out, or do they just keep walking through? And so there was a lot of research that we felt could be accomplished by putting cameras out there, but also by putting HPC right down in the box. An example of that would be, we're talking with the transportation group at Argonne about adding the radio that's used by vehicle to vehicle and vehicle to infrastructure, which is an acronym I can never remember. DSRC, I think is what it is. So adding a radio like that where we, right down on the surface, could listen to the chatter between the vehicles and maybe even make some real-time decisions at that intersection, or at least support people to develop the kind of systems that could make real-time decisions. And if we have to always send the data back to the cloud before we make a decision, the answer comes back too late to actually take the action you wanted to take. So we decided to build a platform that would actually allow people to embed AI and deep learning capabilities right within the platform. That's a stylized example of one of our images for the privacy policy, which we'll have to amend. We can't show the images from the cameras, but you can sort of see the field of view of one of the cameras there. And the idea is to put that computation right down there so that people can do image processing, sound processing right there in real time. So this brought us to the point where the project got unexpectedly way harder. There have been a couple of those points. So most of the sensor networks that you see are kind of like this one here. That's our sensor board on the left, and it allows us to inject a new sensor from a company or from a research group into that little area where the blue arrow starts. And with about a 9-week turnaround, we can add a sensor to that very simple board. It also has a processor on it that's very reliable in heat, in cold, and dust, et cetera, et cetera. So you can make one of these and just have it transmit its stuff back to the cloud And that's pretty easy to do. Probably many of you in the room have done that. I certainly have done multiple of these kind of projects. And the reason is because it's a simple system. And you want, if you're going to put something up on a street pole and pay union laborers about $1,000 a pole for the time to put it up there, you don't want to send them back out there to press reset buttons. So if you want to put these out, in the Arctic or in a city, then you really want a reliable system, and that means like a mean time to failure of years, not months. Now, when we add the Linux devices to the system that are remotely programmable, then you know from doing an uptime on your laptop that does not have a mean time to failure of years if you're going to program the device. And so this is when the project took a turn which we think was ultimately what we wanted to do, but also caused us to learn a lot of lessons in engineering. So what we did was, since we couldn't rely on the Linux boxes for reliability, we built a platform or a harness with those kind of simple processors and some logic that would allow us to recover from failures of those Linux devices, and there are 2 of them that you can see here, and even prevent some of those failures. So as a very simple example, we have current sensors. If one of those devices starts to really suck a lot of current, we can just reboot it with those black boxes at the bottom of right above the word Odroid are relays. Another is that we've got a heartbeat monitor, so we know if a device is wedged, we can reboot it. A third example would be, let's say this aluminum box that we have with these things in it is getting hit by the Chicago August sun, and it gets to be 150 degrees inside the box. Well, we have thermistors inside there taking temperature in 5 different places, including the CPUs. We can go, okay, it's time to hibernate because it's too hot to run. So we tried to anticipate, and I'm sure we didn't get them all. It's whack-a-mole with single points of failure. We tried to anticipate many of those common failure modes and then build them into the system. And this is the 3rd generation of that system that's going up right now in Chicago. We'll do a 4th generation next summer and a 5th generation before we're done. You can go to the Array of Things website, but this is just a list of the sensors that we have now. Air quality, 7 different gases, particles, accelerometers. There's a camera pointed down at the street surfaces I showed you. There's another one pointed straight up, as well as an IR infrared sensor and ultraviolet sensor. So now a temperature reading needs to be interpreted along with ambient light, and is it a cloud cover, is there an oak tree hanging over it? So we have a much better context for reading any of those individual sensors, and then we can start to think, because we will put the Berkeley Cafe system on this, we have open CV libraries now, start to think of this as a autonomous device that has a bunch of senses like we do, and ask it to learn what it should be collecting, what it should be measuring about an intersection, for example. So this is what it looks like on the pole and sort of broken out with 2 different components. One is the processing platform, and the other is a Stevenson shield to hold the sensors that allows air and light to flow through, but not direct precipitation or direct sunlight on the sensor boards. You can see that harness right next to the words open source, aesthetics, quick replace, and resilient. Right next to those on the left is the harness that hangs those sensor boards. The black thing there that looks like a cigar is a microphone. You can see the camera in the bottom left that's pointed off at an angle. Then on the left bottom of the picture there, you see all of the guts of the computing and resilience hardware that are packed into that box. These are direct wired. And we're often asked, well, when are you going to do the battery-powered version? And the answer is we might not do a battery-powered version, because we would rather increase the computation power than sacrifice computation so that we can do a battery-powered version. The problem with increasing computation power that we're starting to address right now is cooling. We're doing passive cooling right now, and we want to move to active cooling. So the partnership with the Department of Transportation electricians, who you see at the bottom of the screen here, began about 2 years ago. On that previous slide, I mentioned flexibility. That means that our goal with the whole packaging of this system was that those guys could go up, one of them in a bucket truck, and you can see in the right-hand side there are 2 stainless steel straps holding it to the pole, and that yellow wire is a screw-in connector. So with the same amount of labor and cost as replacing a holiday wreath, we can replace the entire unit. And that's the strategy for flexibility. We want to add a new sensor, we'll just swap out the whole unit. And that means the electricians can do what they're good at, which is plugging stuff in and wiring stuff and not have to worry about opening up a box and inserting new things and maybe having to do tests to make sure it works, et cetera. On the left, you see that the deployment of these is really a series of experiments. And this is the first 40 that you see on that map there. But they're discrete experiments where we're working with areas of the city where we have three things that come together. And this was, I'd say, another unanticipated lesson of the project is that it's one thing to build a scientific instrument in the lab. It's another thing to put it in people's neighborhoods, especially if there's a camera on it. And so we needed to have a way to partner with the residents of the city of Chicago. And the way we did that was through public meetings and public engagement. And we were looking for concerns on the part of residents, like air quality or traffic safety or flooding, and then saying, okay, that's in the Pilsen neighborhood where you see those stars in the southwest part there. There's an air quality issue there. There's a interstate highway, a 6-lane Stevenson Expressway that goes right through between those Pilsen and McKinley Park neighborhoods. So we said, let's do air quality there because that's a concern on the part of the residents. We also have scientists at UChicago and elsewhere. They're studying asthma. There's a charter high school there, a Latino charter high school that we partnered with that is focused on healthcare professions. And then as far as government goes, the city of Chicago was interested in adjusting and doing green space over there to improve air quality. So when those three things come together, we feel like we have the ingredients for a successful experiment in the city. And the 500 nodes will be ever-increasing size of those kind of experiments. In fact, these first ones that we're mounting, we are experimenting also with how high on the poles they need to go, how close they need to be together, as well as just the resilience of the platform itself. The schedule, I'll just sort of skip through this so we have time for Q&A. The idea is to have these sort of launch windows where we can install new sensors, new microprocessors perhaps, update the hardware. And we just put 6 of these in August as a test of the whole mounting procedure and how to work with the electricians. Based on that, they've gone ahead and pre-wired another 40 or so intersections for us. And within a week or so, we think we'll have debugged yet another sort of unexpected lesson learned that building 50 gadgets in your lab is not the same as having someone build a sort of open-ended number of units outside your lab. So we think we'll have debugged that pipeline in a week or so, and we'll get another 70 in this year and some more in the spring, and then launch windows in the spring this year, next year. I'm going to close by saying 2 things. One, we have been contacted about a rate of 1 or 2 per week of contacts from universities or cities or national laboratories that want to pilot this technology. So we've had to say, oh, okay, well, not just 500 in Chicago. How do we help people do pilot projects? And here you see the red ones are going to be in sort of January, February. The blue ones, we hope, by later next year. The yellow ones are initial conversations. And the idea here from a science point of view is imagine you have this sort of consistent way of measuring cities in experiments like I described, and you're pulling all the data together, open, free data for the science community. That's the science goal of doing all this measurement. So I'll close by saying there are ways that these pilots, and if you're interested, there are ways we want to be working with the community. We had a workshop in September looking at disruptive sensors. If you or one of your colleagues is working on a new sensor, we're interested in the possibility of putting it into that board in the spring of this coming year or later if you're not ready yet. We also are looking for people that are doing deep learning, AI, computer vision, audio processing that will want to develop on this platform. As I said, we have open CV libraries now. We will support Café. And then pilot projects like I mentioned in the map before. So there are lots of ways that we would love to interact with the community. We found that there are a lot of groups that are doing innovative stuff on platforms like ours, but there are even more groups that just want to use a platform and get it out there or maybe modify it for their use. So it's all open source hardware and software, and that's what we're trying to do is provide a platform to the community and a sort of foundry in Chicago with 500 of them being refreshed to try things out at scale. I'm going to stop there and turn it back over to Liz for questions if anyone has any. Thank you.
We did have a few questions posted, which we can get Charlie started on. If others in the audience have questions, there are microphones in the those two aisles there. And so one of the questions that we got online is, how do you address the surveillance concerns of residents?
Good question. So you might have noticed a surveillance camera right under one of our units in one of those pictures. Chicago has, depending on who you ask, between 15 and 25,000 cameras already. But for some reason, because we were working with the city, our cameras got a lot more attention. We've addressed it a couple of ways. Technically, what we've done is the normal operation for these devices will be to process the sound and images inside the device and then delete the images and the sound files after a few minutes and send the extracted information back, which also, by the way, saves bandwidth. We're using AT&T as our provider for cell phone connectivity. That's how we connect these. On campus, they're Wi-Fi. But the second is transparency, and we did the privacy policy with a draft that started with a working group that included security and privacy experts from universities and cities and EFF and ACLU. And we rolled that out through a public comment period online, public meetings in libraries, to be fully, sorry. My question was, is there water somewhere?
Oh, shoot. Yeah. Do you want me to get my water bottle for you?
I'll try to work through. The third was, accountability. So we got the NSF to, I better take a drink of water, I'm sorry. Thank you. I do love this stuff and I get choked up, but that wasn't that. It was just dry throat. We run the devices technically to protect security or privacy. We went transparent. And third, accountability, which is a group at Indiana University led by Von Welch, has audit ability, and so it's built into the governance. And we find that people are generally okay with surveillance of their neighbors, just not of them.
All of a sudden, lots of questions are coming in. How did you select the locations for your sensors?
So that, I could go back to, so that is where we look for a community concern, a science group that's already funded to do research there, and a city official like a department head or commissioner that is saying, if we get insight into that problem, we actually want to do something about it. And that's an evolving thing. There's a web form that people can fill out.
And one that's perhaps a little bit more technical, how do you manage storing the time series data from the sensor network?
So storing the data, that's an evolving, the sort of data pipeline. Right now we're concentrating on APIs. All the data is going into a database, a Cassandra database. We're pushing it out to the city's open data portal, which is a Socrates system, pushing it out to Planario, the animation that I showed you. But we're really concentrating on APIs so that others can take the data and repurpose it in ways that are conducive to the particular questions they're trying to ask.
Do the sensors measure noise levels? I think that would be an essential quality of life measure for city residents.
Yeah, noise, they do. The microphone does noise levels, but it also will support audio processing to say, well, what kind of noise are we hearing? Is it a siren or a car crash or what have you?
There's one, I don't exactly know what this means. Have you tried interfacing with ShotSpotter?
No. So ShotSpotter is a system Chicago and other cities have with microphones that can triangulate on a gunshot. And we will certainly be able to pick up a gunshot. There's no need for us to do ShotSpotter because it's already there, but it would be possible if somebody wanted to do it. We have stayed pretty clear of the operational infrastructure of the city and of policing, et cetera, partly because of the perception issues and wanting to be more not a device the city is putting in your neighborhood, but a device the University of Chicago and Argonne are providing to your neighborhood.
And so do you think that the residents of Chicago appreciate the research value of this work?
You know, it's even within neighborhoods, it's hard to say what the residents' view is, you know, because everyone is different. We found in our community meetings where we had between 40 and 80 people were there for the evening, and we had a meal and presented and did a Q&A with them, that people were just really curious about, you know, air quality and even like this one woman from the Pilsen neighborhood, she's like, you're going to put them all at 22 feet, but is that going to tell me what air quality is like down at 5 feet where I'm breathing? And so they were asking the same questions that you would expect from a science workshop. So we found that people in the city are actually very interested in the science, and they're especially interested in the science if their kids can get involved.
That last question was from me. I believe that we've handled all the questions here on ours. If there are any other further questions, you can either type it in there or run up to one of the microphones. We're down almost to our very last seconds here. Okay, well, let's thank our speaker again.